So, hello everyone. Let's continue from tomorrow. Sorry, from yesterday, where we left. Now, today's topic will be torque on a dipole of a uniform in a uniform electric field. So, we are going to derive the formula for the torque on an electric dipole when it is placed in a uniform electric field. Right? So, torque, we all know that means which produces a turning effect. When a dipole is placed in a uniform electric field, say lines are parallel to each other, and here it is a dipole which is placed like this. Fine. So this dipole will move in this field. Actually, it has to, then it is translational movement. But this dipole creates, the torque is created on it, and this dipole moves like this. We need to find this formula, torque. This is the torque. Right? So let's consider dipole with two charges, positive q and negative q, separated by a distance. We know that the distance is say 2a, and it is placed in a uniform electric field, which makes an angle theta. Let's say this is a uniform electric field. There is a dipole, right? Let's place this dipole over here. So here it is plus q charge, this is a minus q charge, and this distance is 2a. Fine. Now, this is positive charge, so electric force due to this will be in this direction. This is electric field. So fine. So this electric force is q times e, and here it is negative charge. So this will be in this direction. Because it is negative charge, it will move away from it. So this is QE minus. This is minus QE. So net force, which is acting on this dipole, is total force, F total. This is equal to force due to plus Q charge, fine, and while in the force due to negative charge, fine. So this is minus so this force is Q times E minus Q times E. This is resultant. So resultant force is 0. This resultant force is translational. Fine. But here the torque, on torque, so we need to find that force. Fine. Translating force we have found to be 0. Fine. So as these two forces are equal and opposite each other, they will form a couple. They form a couple, they will rotate this dipole like this. They are creating the torque on it. So torque will be either force into perpendicular distance, either force into perpendicular distance between the two forces. So the perpendicular distance between these two forces will be this one. This is theta, right? This theta is between the electric field lines and the dipole. This is the perpendicular distance. Using trigonometry, this will be 2a sine theta. 2a sine theta. Now, torque is, this is tau, this is torque, that is equal to either force into perpendicular distance. This is equal to either force means we may have QE into perpendicular distance, 2a sine theta, right? 2a sine theta. Now, 2aq, if we arrange it like 2aq can be arranged like this into E sine theta, right? So this is dipole P E sine theta. This formula is reduced to PE sine theta. Fine. In vector form, this is P cross sine theta, P cross E. Right? This is the formula. Right? And the direction is that in which right-handed screw rule. Right-hand screw rule will give us the direction, or we may say, if I'm holding this like this, right-hand palm rule is also there. This palm will give me the magnitude and the point in which this pen is pointing. That gives us the direction of the vector. The direction of the vector. Fine. So now it depends upon sin theta also. The torque due to dipole acting when it is placed in a uniform electric field depends upon three factors. One is the dipole moment itself, then electric field, and the theta, sine of theta. So torque will be maximum when value of sine theta is maximum, which is at 90 degrees. So if theta is 90, we have torque is equal to P cross E. With P into E sine 90, which is 1. So that is torque into PE, which is the maximum value of the torque when it is exerted. Now comes, let's move ahead. Now, the electric field lines, some properties are to be discussed about this. Electric field line, here they can be defined as a curve along which a small positive charge would tend to move when free to do so in an electric field. And the tangent at any point gives us the direction of the electric field. Suppose this is the curve, here is the point, this gives us the direction at this point. This gives us the direction of the electric field. Right? Lines of forces, they are always continuous smooth curves without any breaks, first thing. Lines of forces, they start at the positive charge and they end at the negative charge. They cannot form closed loops. If there is a single charge, then the lines of force will start or end at infinity. Tangent to any line of force at any point gives us the direction of the electric field at that point. Then no two lines of force can cross each other. This point is very important, and on this questions are also asked in 1 markers. Why no two lines of force can cross each other or can intersect each other? If they intersect, what will happen? There will be two tangents drawn at the point of intersection, and hence two directions of the electric field at that same point, which is not possible. Which is not possible. So lines of force, they are always normal to the surface of the conductor on which the charge are in equilibrium. So if the line, this point is also very important to be noted, because the questions can also be asked on this. Why line of forces are always normal to the surface of conductor. If the lines of force are not normal to the conductor, then component of the field which is parallel to the surface would cause the electrons to move and would set up a current on the surface itself. But in an equilibrium condition, no current flows. So that is why it has to be normal orbit. Lines of forces, they always have a tendency to contract lengthwise, which explains the attraction between two unlike charges. Lines of force always have a tendency to expand laterally, sidewise, they expand, so as to exert a lateral pressure on the neighboring lines of force, which explains the repulsion between the two similar charges. And we can calculate the strength of electric field by the relative closeness of the lines. More closer they are, that means stronger is the electric field. If they are far apart from each other, that means weak electric field. And if the lines are parallel and equally spaced, that means if the electric field is uniform. And one more important thing, electric lines of these force do not pass through a conductor, because electric field inside any charged conductor is 0. So if we are to draw lines of electric field. Suppose that we take the spherical charge first. So here is the same positive charge. Electric field will be like this, outwards. And if it's a negative charge, it is inverse. Right? And suppose there are two positive charges placed in front of each other, then electric field line would be like this. This is positive charge, this is positive charge. Right? Here there will be a repulsion. So electric field lines will like move like this. Based on these questions may be asked, what happens if there are like now there's a positive charge and a negative charge. This is positive, this is a negative, right? Electric fields, we know they move from positive to negative. It will go like this. Okay? And we can have like this. When one charge is positive, other is negative. Now, what if there is a positive charge placed? There is a positive charge. Electric will move like this uniformly away from this plate. Right? Now, okay. Now, we're going to start with the topic electric flux. Before that, we should know something about the area vector, which is of very importance. Area vector, suppose there is a conductor. Let's say this is conductor, and we have an area vector which should be perpendicular to this. So say this is the random and we have taken this part only, right? So the area vector will be perpendicular to this. Fine. It should be normal outward from the conductor. So the direction of area vector is always specified by the normal to the plane. We can say that. Now electric flux so the term flux means some kind of flow. And flux is the property of any vector field. So we are to define the flux through a given area. When it is held in some electric field, it can be measured by the total number of electric field lines which are passing normally through that area. See, suppose we have these are number of electric field lines, and it's a conductor. Fine. So these field lines are passing normally through it. So all lines are passing. If we turn this a bit, then number of field lines passing through this area of cross section will be reduced, and here almost zero. Then again, if we turn this, the number of electric fields then will increase, and it will be maximum when it faces it normally. Now, suppose the area vector is like this at some angle. So electric field, which were to be considered, it should be always a perpendicular to this surface, like this. So this is going to be a component vector. Here it is. So there is an angle. Fine. So there will be angle between these two. Initially, we are considering the uniform electric field in the direction like this, and the area vector is at a certain angle. Fine. And the component of this electric field, which is perpendicular to this area vector, is considered. So then number of field lines changing through it will also depend upon the theta that we consider as cos theta. electric flux is denoted by symbol phi. This is phi, electric flux. So electric field passing through area EDS. Well, let's say delta S. Fine. You can consider it as delta S. So when through some angle, means see this is a surface. Fine. So here it is, we have the electric field. Right. So this is theta, and this component is E cos theta. E cos theta. Now flux will be, we have E cos theta into S. E cos theta delta S. Fine. Or we may write, see, there is a cos theta involved, it's a dot product. So we can write it in the form of dot product as C E delta S cos theta, or this is E dot S. E dot delta S. So it's in the form of the dot product. So let's look at the sign of this. This is flux. Electric flux. That means change in the number of, we can also define electric flux as change in the number of electric field lines passing through unit cross section area perpendicular to it. Then based on this, first of all, we need to find, if you are asked to find the units of electric electric flux. So this is Newton per Coulomb. Fine. So Newton per Coulomb into area, units of area, which is meter square. That is Newton per Coulomb meter square. These are the units for the electric flux. Or we may also have electric field के unit is volt per meter भी होता है into meter square. So that means volt meter is also the alternative unit used for electric flux. Then comes the Gauss theorem, which is very important topic. 2 markers must be asked about this. Right? So Gauss theorem states that the total flux through any closed surface is 1 by epsilon naught times the charge enclosed in it. Just hold on for a moment, please.
Sir, you're not audible.
Purchase of investment. What do you mean by purchase of investment? Purchase of investment means it can be shares. You are investing in shares.
Hello. Yes, now you're audible.
Or you are purchasing other companies.
Okay. Okay.
Or you will be depositing an FD somewhere. Whenever we deposit.
Hello, ma'am. Is there any problem?
Now you're audible, sir. You weren't audible.
Oh,
Whenever we
I'm audible now?
Yes. Yes. Please continue.
Okay. So this is 1 by 4 pi epsilon naught q by r square. And here it is. We calculated, substitute the value of E and 4 pi r square. Cut 4 pi r cut, r square cut, and we got, then we get the q by epsilon naught. So this is the proof of the Gauss law, which is 1 by epsilon naught times the total charge q enclosed in this closed surface. We can also derive Coulomb's law from this Gauss law. Let's derive that. Let me just rub this side. See, again considering this positive charge, we draw a Gaussian surface around it. We have an area element, so ds. Electric field on this area element is moving radially outwards. Similarly, the area element also moving radially outwards. The angle between them is again theta, right? So the flux through this area element ds, this is equal to EDS cos theta. This is EDS up to here it is same. Fine. So net flux through the closed surface will be equal to the surface integral of this. We did E delta ds, which is E by 4 pi r square, right? Now, instead of going for this step, what we'll do, we know from the Gauss theorem, the flux is also Q by epsilon naught times. The flux, so according to Gauss theorem, we have flux is equal to Q by epsilon times, and what we found is E pi r, 4 pi r square. This is the flux which is found by us. So this is equal to E is what? This is the flux. Now we can equate these two values. That means E electric field into 4 pi r square. This is equal to Q by epsilon times epsilon naught. So this E is 1 by 4 pi epsilon naught Q by r square, right? 1 by 4 pi epsilon naught into Q by r square. Sorry, Q by r square. Fine. E is Q 1 by 4 pi epsilon naught Q by r square, right? So here is okay. E is this. Now force acting on this test charge. The force acting on test charge. Q naught. Force acting on test charge Q naught, which is placed over somewhere here. Q naught, right? Test charge Q naught. That is equal to F is equal to E into Q naught, and the value of E is equal to what? 1 by 4 pi epsilon naught Q by r square into Q naught, right? So which is nothing but Coulomb law. Q naught by r square. That's it. That's a derivation of Coulomb law from Gauss law. 2 marker questions. Right? And there is one very common question which is asked, that suppose we have a cylindrical surface like this is a cylinder, fine, and we are asked to find the electric field or the electric flux through this cylinder. So there are 3 surfaces. Surface number 1 is surface number 2, and this is surface number 3. Or 1, 2, 3. We will take, let's take it 1. This is 2. This is 3. Let us take it like this. Right? So let's say electric field, direction of electric field is in this way. So for this first surface, right, this is its area element, and the electric field goes against it. This is electric field, this is the area element. So the angle between these two is how much? 180 degrees. Here is the area element we are considering. This is electric field, and this is the area element. Yes. So this angle is 90 degrees, and here we considering this is the area element ds, and this is electric field. Here cos theta is 0. Here it is 90 degrees. There are 3 surfaces. Total electric flux can be calculated by adding all these. Fine. So this is equal to total flux will be equal to integration of EDS at first surface plus second surface EDS at third surface. Sorry. Right? This is EDS. Now, angle between these two is 180 degrees. So, how will we do? Cos theta we know is 180 degrees. So, we can place this value as EDS into cos 180 here. Let us write cos 180 over here. Plus EDS into cos 90. And EDS is equal to cos 0. So this is minus 1. So this will be minus EDS. Plus this is 0. This is 1. So this is EDS. So this minus minus gets cancelled. The total flux will be 0. Hence it is proved that the total flux through a cylindrical is 0. Cylinder is 0. Clear? So let's move to some other thing. There's a one question which is very commonly asked. They'll give some random figure and charges will be there. So like I'll draw the figure for you. So let's say any shape. So there is a 1 rupee coin, 1 rupee coin. Fine. There is one charge, positive charge. Another charge is say this is negative. Here it is negative. Then this is positive, right? So this is say Q1, again negative. Q1, this is Q2, then it's Q3, Q4, and say Q5. Now there are 4-5 charges given to us. The magnitude of these charges is Q1 is equal to this is Q4 and this is Q5. So Q1 and Q4 they are equal to 3.1 nanocoulomb. Then Q2 and Q5 this is equal to minus 5.9 coulomb nanocoulomb, right? And Q3 is given minus 3.1 nanocoulomb. We need to find the net electric flux through this. So there is nothing, the coin is neutral. The closed surface, in the closed surface, we have 3 charges, Q1, Q2, and Q3, right? And Gauss law says that the total enclosed charge should be there. See, flux is equal to 1 by epsilon naught times the net charge, and which is kept enclosed in a closed surface. So net charge we need to find of these 3 charges, which is Q1, Q2, and Q3, right? So using Gauss theorem, we get flux is equal to Q, what Q? That is Q1 plus Q2 plus Q3. So this is Q by epsilon naught, or this is Q1 plus Q2 plus Q3 upon epsilon naught value, right? So Q1 is given 3.19 nanocoulomb, Q2 is given minus 5.9, and Q3 is given this, which is minus 3.1. So simply adding it, so 3.1 minus 5.9 minus 3.1 whole into 10 to the power minus 9 upon value of E naught is 8.85 into 10 to the power minus 12, right? Now, by solving it, we can easily get the answers. So this is which is that will come out to be so minus 666.67. 666.67 Newton per coulomb per meter square. Per coulomb meter square. Second answer. Now, there's one more. Now, if we are asked to find the electric field due to an infinitely long straight charged wire, what is to be done? Simple. We'll consider a linear charge. Fine. And see, now we have to find what? Electric field due to infinitely long straight conductor. Electric field due to infinitely long conductor. Let's say here we have a current positively charged conductor of infinite length, say. Fine. Now we'll draw a Gaussian surface around it. It's a Gaussian surface. Fine. It's a Gaussian surface. See, in this again, we are having three phases. Area element of this surface is this way. Because this is positive charge, electric field will go in this direction and this direction. So three faces are there. One is this is the second curved face, and this is the third bottom face. Here we have area element in this direction as well as electric field in this direction, right? And in this case, we have area element perpendicular and electric field is in this direction. And on this surface, we have area element in the downward direction, but electric field is still in this direction. So these total flux we need to find at three surfaces. First surface, ED, A cos theta is 90 degree here. Here it is 0 degree, EA cos theta, cos 0. Here it is again 90 degrees. Fine. So what do we have? Flux is, total flux will be equal to the sum of these three surfaces. Fine. So this is surface 1, surface integral EDS, right? Which is EDS cos how much? 90. Fine. Second surface, we have surface integral EDS cos 0. Third surface, EDS again cos 90. Cos 90 means 0. Right? Here E will be out. We have BS. Cos 0 is 1 to EDS. Here we have cos 90 again 0. This is again 0. Right? So now this is DS. DS means area of this curved surface. Because here this surface we have 0, this surface 0, and the curved surface part, this is a state, suppose this is a wire, cylindrical part. At this surface it is moving, the area element is in the upward direction, electric field is towards me, here electric field is towards me, and the curved part is there. This is, area element is moving in the downward direction, electric field is still towards me. Here angle between the area element and electric field is 90, so it being 0, it is also 0. So total flux will be due to this curved path. EDS. So what is DS now? DS is the total curved path. total length, which is circumference of this. So that means 2 pi r. Right? So this flux is equal to E into 2 pi r L, which is the length of this. Right? Now, what is the flux according to the Gauss theorem? Gauss theorem says flux is Q by epsilon naught. So, according to Gauss theorem, flux is Q by epsilon naught. So, this is equal to Q by epsilon naught is equal to E times 2 pi r L. Because we are considering the length of a conductor, and yesterday we did length charge density, which is denoted by lambda, right? So, what is that? So, lambda is equal to Q by L. Length charge density lambda, this is equal to Q by L. So total charge will be 2 lambda times L. Let us replace this Q by lambda L. So we get lambda into L by epsilon naught. This is equal to E 2 pi R L. Right? So electric field will be E is equal to lambda L by epsilon naught into 1 by 2 pi R L. L goes with this. Fine, because this is the same length. We are left with lambda upon epsilon naught or 2 pi epsilon naught R. This is the electric field of a line charge, right? Or of a conductor of infinite length. And here we see that the electric field of a line charge is always inversely proportional to the distance from the line charge. Because here R is in the denominator, as we move away from the surface, curved surface, R goes on increasing. So strength of electric field goes on decreasing. Now let's find for the sheet. If we are given a plane sheet, and we need to find the electric field of a uniformly charged plane sheet. Right? So let us draw a diagram for that. I'm going to do this. So this is electric field due to uniformly charged infinite plane sheet. Infinite plane sheet. Right? So let us say we have a sheet which is positively charged. Right? Now we need to consider a Gaussian surface. Fine. And we want to find a point, this electric flux at a point P lying at some distance from it. Fine. So let us have the Gaussian surface. We draw the Gaussian cylinder like this. Gaussian surface. We have taken, consider it, passing to it. This is a positively charged plate. Positive charge, electric field will be on this surface. It is called away from this, and this sheet is like this. So here is the Gaussian surface. We can see that this pen. Let us consider this as a Gaussian surface. The surface is perpendicular to this, and electric field. The charge on this is positive. Electric field will be towards mine, and from this phase, it will be on the other side. So this is electric field, and this is electric field. Moving away from this. Fine. So here, let's say it's point P on which we need to find the flux. Right? So area element is in this direction. Here also area element is in this direction. Theta will be 0. Here also theta will be 0. Right? So total flux due to these two surfaces will be equal to, what is the formula? That is EDS cos theta. Fine. So EDS cos theta is 0. So this is, we will say ES. Surface integral करेंगे इसका, and we get EDS, which is equal to ES. Let's say this is for this surface, and this is for this surface also. It will come equal to this, because in this also area element and electric field, they both are moving away from the sheet. So angle between them is 0 degrees. So cos 0 is 1. So here we also get flux as ES for first surface, and this is for second surface. Right? So total flux is addition of these two. This means ES plus ES, that is equal to 2 times ES. 2 times ES. Or we may write A also. Let's say A is the area of cross section. We may write A also. Now, or 2 times EA, which is S, which gives us S, because S is equal to A, that is area of cross section. Right? This is a circular path. Charge is distributed over the whole area. Surface charge density will be there. The surface charge density will know that it is denoted by sigma. Sigma is equal to total charge distributed over the whole area, or Q is equal to sigma times A. Right? Gauss theorem flux, according to Gauss theorem, flux is equal to Q by epsilon naught. This is equal to 2 times EA, 2 times EA. Right? It's 2 times EA. Now this Q is to be replaced by sigma A upon epsilon naught is equal to 2 times EA. Right? This A goes with this. So we have electric field equals to sigma by 2 epsilon naught. Right? This is the formula. Find the electric field due to uniformly charged plane sheet. Right? So we know that in this formula there is no R. We don't have any distance. So if the sheet is positively charged, that means surface charge density is greater than 0. The field is always directed away from it. And if the sheet is negatively charged, fine, the field is directed towards it. Now, what if the two sheets are given? What if the two sheets are given of uniform charge densities, right? We need to find the electric field at different points. So let's say now electric field due to two positively charged parallel plates. So let's draw the diagram for this first of all. Here is sheet number 1. This is positive charge. Parallel to this, another sheet is placed. So this is plus, plus, plus. Right? So it has surface charge density, say sigma 1. Let this be sigma 2. Plate number 1, plate number 2. Now electric field due to this, it is moving this way. Right? That is E1 here also it is E1, right? In between, this is away from it, E1. Fine. So let's say this is the first part, so second part between the two sheets. This is left of the one sheet and this is right on the second sheet, third part. Fine. Then electric field E2, due to this, it is in this direction. E2, here it is E2. Fine. And this is E2. Right? Now, this is the separation between two, like this we say R. Now, in the region 1, what will happen? We have just calculated that the electric field due to plane sheet is always sigma by 2 epsilon naught. So E1 will be equal to, this is for the region 1, right? First part, that is toward the left of the sheet. E1 will be equal to, so because it is moving toward the left side, so let's place negative sign. This is sigma 1 by 2 epsilon naught. So R vector will be there because this it shows that the position of this sheet from this is relatively distance between them is R. So R cap. Then E2. E2 we have again sigma 2 by 2 epsilon naught R cap, right? So what according to principle of superposition, these two electric fields need to be added. So E1, E जो है, that is equal to be E1 plus E2. So E1 plus E2. If we add them, we get minus R cap upon 2 epsilon naught. This is sigma 1 plus sigma 2. Now in the region 2, that means in between these two parallel plates. In these two parallel plates, we have E1. This is equal to right side sigma 1 by 2 epsilon naught R cap. Then E2, it's on the left of this, so it should be minus sigma 2 upon 2 epsilon naught R cap, right? Total field will be addition of these fields, that is E1 plus E2. That will give me, what will be the answer? So R cap upon 2 epsilon naught. This is sigma 1 minus sigma 2. Now in the third region, that is this way. So third region we have E1. This is again positive. E1 is equal to sigma 1 by 2 epsilon naught R cap, right? And E2 is, this is has to be positive, right? So this is what? Sigma 2 upon 2 epsilon naught, this is R cap. So total electric field will be equal to E1 plus E2. We get R by 2 epsilon naught sigma 1 plus sigma 2. This is the total electric field. Now, if these two sheets having a same or similar charge density, so what is then total electric field? That's very simple. Here sigma 1 equal to sigma 2 is equal to sigma. Put that. And for the first part, this will be R2 pi epsilon naught sigma plus sigma. This is 2 sigma. 2 gets cancelled with each other, right? So in the region of this, we can have wait, just wait. here we have considered this positive. This is, suppose this is negative now. For the second case, let us consider this negative, so this will become positive. So it will be 0 here, and these two will give us, second part will give sigma by epsilon, 2 will get cancelled, and the third part, which is on the right side, that will give us again 0. So there is only one topic left in this. That is about the uniformly charged sphere, which we can do in the next class probably. That's all for today.
Thank you, sir.